Hi guys, today we are going to be doing a little introduction to the next topic in Unit 6, which is scientific notation. So how do I represent a number in scientific or in standard form, scientific notation, and in technology displays? So the neat thing about scientific notation is this is actually a topic that, depending on what field of work you go into after high school, you could see this. Oftentimes, it's used in any kind of science field, any kind of medical field. When you work with very tiny numbers, very small, minuscule numbers, you see scientific notation, as well as even some business classes, like accounting, that kind of stuff. Anywhere where you're going to work with really large numbers, you'll see scientific notation as well. So, first bit of vocab/notes is standard notation. This is just the normal way of writing numbers. How you would normally write a number, that is just standard notation. Scientific notation is a method of expressing very small and very large numbers. For instance, numbers that have lots of zeros at the end. A shorter way of writing that is with what we call scientific notation. Whereas very tiny numbers with lots of decimal places, lots of zeros in front of the decimal places, or after the decimal places, we can use scientific notation to represent that. So it's going to be a little confusing at first, but it is typically written as a product of a number that is greater than or equal to 1 and less than 10. And as a power of 10. Okay, that'll make more sense when we get into some examples down here below. And then technology display is what your calculators might do. It's the way some calculators display very large, very small numbers instead of scientific notation. It's the same thing, it just looks different in some calculators. Alright. So for these example displays, we are going to kind of talk about these one at a time and how it works. So examples of these three displays. All right, so if we're talking about sea creatures, okay, the first sea creature I want to talk about is a blue whale. So the weight in pounds, in standard form of an average blue whale, would be 250,000. I forgot how to say it for a second. 250,000 pounds. We can express this number, 250,000, in scientific notation as 2.5 times 10 to the power of 5. So all this is the number 2.5 times 10 to the power of 5. Okay? So one way to think of that is scientific notation, pretty much this 10 to the power of 5, is how many times you would have to move the decimal to get it to 2.5. So if we think of this number, right, there's a decimal typically right here. If I wanted to move this decimal 1, 2, 3, 4, 5 times, it would put it at 2.5. Since I moved the decimal 5 places, that's like times 10 to the power of 5. Okay, because hopefully you know anytime you multiply by 10, it moves the decimal one spot over. So the technology display would be 2.5 EE5. So it's the same thing. If you see EE, it's just like times 10. Okay, so 2.5 EE5 is the same as 2.5 times 10 to the power of 5. Right. Gray whale, same idea. Okay, a gray whale is on average about 68,000 pounds. Instead of writing out 68,000 pounds, you could write 6.8 times 10 to the power of 4. Okay, again, that times 10 to the power of 4 just means if I wanted to take 6.8, I could move that. If I write it, take 6.8, I could move it 1, 2, 3, 4 decimal places to the right, because it's times 10 to the power of 4. You would get 68,000. It's just another way of displaying a really large number. Honestly, 68,000 is not a huge number, but you can work with some really big numbers. Like I could make this, for instance, if I wanted to say like 7 billion, right? Be 2. Right, 7 billion. A lot of zeros, very big number. Okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 zeros there. I could express that as 7 times 10 to the power of 9. Okay, those two are the same thing. Okay, scientific notation is just a much shorter and much faster way of writing really big numbers. Again, so for example, like what if I wanted to take this times 4 billion? 2. Right? If you would multiply those together, you'd get a really, really, really big number. Just as a little pre-introduction to you, you can do that. You would get 4 times 10 to the power of 9. You can multiply scientific notation. This is why it's useful, especially in a lot of jobs that deal with big numbers. That just becomes 28 times 10 to the power of 18. And technically, if we're getting a little bit farther here, that would also turn into 2.8 times 10 to the power of 19. Okay, we'll learn about how you multiply all this stuff later in the future. This is just me giving you examples of like how this is actually used. Okay, so instead of writing 19 zeros after the 2.8, we can just write it as 2.8 times 10 to the power of 19. And there are a lot of jobs that deal with numbers this big. Okay. And the last example here, whale sharks, 41,200. If my decimal point would be here, scientific notation, we always need to move that decimal point right before or right after the first number. So it'd be 4.1 times 10 to the power of 4 because I moved that decimal 4 times. Right. So when it comes to writing a number in scientific notation, to translate between standard notation and scientific notation, you can just count the number of decimal places the decimal point moves. So when it comes to writing large quantities in scientific notation, when the number is greater than or equal to 10, we use positive exponents. So again, if I want to make sure my decimal point goes in between the 8 and the 4, okay, the decimal point always wants to go after the first number. So it's going to be 8.4. We know to get back to its starting position, we need to move it 1, 2, 3, 4 times. So it'd be times 10 to the power of 4. The decimal place moves 4 places. Whereas when it comes to writing very small quantities in scientific notation, when the number's between 0 and 1, use a negative exponent. So, same idea. I want my new decimal point to be after the first number that's not a 0. Okay, so it's not going to go here. You go to the second spot over the first number after 0. So, I moved my decimal spot 2 places there. So it's going to be 7.83 times 10 to the power of negative 2. The reason it's negative is because I'm dealing with a small number. Any number less than 1 is going to be negative exponents. And I move the decimal spot 2 places over, so it's 7.83 times 10 to the power of negative 2. I don't expect this to feel easy yet. Okay, at the back of your paper, we have a bunch more examples that we're going to do some practice on. Probably do like 3 of each together, and the rest will be on you to try. Okay? So, first one, 4.87 times 10 to the power of negative 2. This first section is going to be a little annoying because we're going to write it in standard form instead, just a regular number. So, first thing I notice is that I have a negative exponent, so I know my number should be small. that should start with a 0 point something. Right? It's a negative exponent, so if you think of number lines, right, if you don't know which way to go, negative numbers go to the left, so I'm going to move the decimal point 1, 2 spots. This is where my decimal should be, which means I need a 0 here. 0.0487 would be standard form. All right. Number 2, this time we got a positive exponent. So I know that my number is going to be big. It's not going to be decimal, it's going to be a very large number. I need to move my decimal 7 spaces to the right this time. Negative exponents go to the left, positives go to the right. So 7.112, I'm going to move it 1, 2, 3 spaces, gets me here. Then I would need to move 4 more spaces to get to 7. If you want to write it out, 1, 2, 3, 4, you can. Or you can just think of, if I have 4 spaces left to go, I'm adding 4 more zeros. So it's 7, 1, 1, 2, then 4 more zeros. 1, 2, 3, 4. So go in and add my commas. That is, what, 71,120,000? Yeah. Hopefully that made sense. Just go over one more time. I'm moving this decimal place 7 spots to the right. I move it 1, 2, 3 spots. I am out of numbers here, so I just replace the rest of the spots with zeros. So for number 3, we have 10x to the power of negative 8. Negative exponent means it's going to the left. So it's going to be this moved 8 spots to the left. So it's going to be 0.1, 2, 3, 4, 5, 6, 7 zeros, followed by 8, 2, 9. Very tiny numbers. Okay, and you can always just double check. Okay, I moved 8 spots to the left, so if I wanted to move this decimal spot back, it would be 1, 2, 3, 4, 5, 6, 7, 8. Puts me back to where I started. Alright. The big exponents can be a little tricky, so just make sure you double check them as you do them. Alright, so you guys will finish 4 through 10, and then check your work with me when you're done. As for the other ones, it's kind of working backwards, where we have to write each number in scientific notation. So remember, scientific notation starts between 1 and 10. So in this number, I want my new decimal spot to be between the 1 and the 3. So to get my decimal here, I had to move it 1, 2, 3 times. So it's going to be 1.334 times 10 to the power of, what do we say, 3 times? 1, 2, 3. Number 12, same idea. I want my decimal between the 8 and the 4. I had to move that 1, 2, 3, 4, 5, 6, 7, 8 times. So it's going to be 8.43 times 10 to the power of, I already forget what I said, 1, 2, 3, 4, 5, 6, 7, 8. Power of 8. Number 13, I see that it's a small answer, so I know my exponent is going to be negative. And I want my new answer to be 6.4. So I have to count how many spots I'm moving. 1, 2, 3, 4, 5, 6, 7 spots. So it's going to be 6.4140 times 10 to the power of negative 7. Again, make sure it's negative 7 because it's a small number. It's not a negative number. So go ahead, finish the rest of this paper. When you're done, please come check it with me. And if you're good, I will tell you what to do next. Bye, guys.